right, so we've already looked at how we can evaluate limits in general, okay, but today we're going to talk about specifically trig limits. So we're going to see sine, cosine, tangent, okay, those basic kind of trig functions. What is the first step in a limit that we usually take? Yeah?
Substitution.
Let's always try that first, okay? So when we substitute in a number, one of three things is going to happen. We're either going to get a number as an answer, which is our limit, okay, so we're basically done, or we can get 0 over 0, which is a whole, kind of signifying we have more work to do to figure out the limit, or we can get a number over 0, which is signifying an asymptote. Okay, so direct substitution is always going to lead to one of three things to help you determine where you need to go from there. Okay, so let's go ahead and try to plug in this case, 2 pi over 3. If we plug in 2 pi over 3 into the first theta value, notice how the 3 from the function will cancel out with the 3 from the value. So we're just left with a 2 pi. And when we plug it into the bottom theta value, the same thing's going to happen, right? The 3's would cancel. So we're just left with 2 pi. Now, since we're dealing with trig, we have to be familiar with the unit circle, or at least the first quadrant. We have to know those, all those points, as well as the top, bottom, left, right. Okay, we have to know those. So sine of 2 pi, the 2 pi location is one of them you have to know. Can we figure out the sine value at that radian location? Sine of 2 pi, that's the furthest to the right. Yeah,
0.
It's 0. And what's 0 divided by 2 pi?
0.
It's still 0, yep. So graphically speaking, as we approach 2 pi over 3 from the left and the right, the height of this graph, whatever it may look like, is approaching 0. Okay, let's go ahead and try the next one. If we plug in pi, pi is another radian value we have to know, and we specifically want the cosine from that pi location. Yeah?
I'm going to guess 2 times -1.
It would be 1, okay, but the cosine value is -1, right?
Oh, yes.
Okay.
Well, it'll be -1 squared.
-1 squared. Okay, so we still need to figure out that trig value based off the unit circle. This time, though, we have a cosine squared, so we're simply just going to square that trig value that we find. So we're left with 2 times 1, or just 2. Again, graphically speaking, if we approach pi from the left and the right, this graph, whatever it may look like, is approaching a height of 2. Okay, so these were easy trig limits because direct substitution seemed to work. Notice how we got a number as the answer, but we know that might not always be the case. Sometimes we get 0 over 0 or a number over 0. So that's what we're going to take a look at today. Okay, so let's try maybe this next one. If we try direct substitution, plugging in 0, on your unit circle, what's the cosine value at 0? Again, that's the furthest point to the right, kind of the one you start at. Cosine, yeah? 1. Okay, so up top we have 1 minus 1. And down below, we need the sine value from that same 0 location, which is just 0, yep. So 1 minus 1 is 0 up top, 0 squared on the bottom is still 0. So notice how this trig limit, okay, is not working out as nicely as the previous two we did. We know that this is undefined, and graphically we have a hole. So we have a little bit more work to do. Now, if you think about the limits that we talked about previously, what are some algebraic techniques that we used to work around that whole issue? H-O-L-E, issue. What, we could factor. If we had square roots, we could use conjugates. If we had a bunch of parentheses, we could try to expand everything, see if anything would cancel out, okay? We talked about fraction work. Like if we had a bunch of fractions, we can eventually combine them into one fraction to see what would happen. Okay, so those same techniques are going to apply, but usually when we're working with trig functions, you're not working with square roots, so a conjugate might not be necessary. Maybe we can expand, but we don't have any parentheses in this case, so we're not going to worry about that. And fraction work, we don't really have many fractions going on here. But the one thing that trig involves that some of the other equations didn't, that we looked at before, are identities. Do you remember those from last year? We've heard of them before, right? I know you went over a ton of identities last year, but there's really only one that we have to know. It's kind of like the mother lode of all of them. So we're going to write that down here. We have to know this trig identity. Does anyone want to take a stab at the one that is kind of the most important? If there's one that you absolutely remember from last year, that's probably it. Sine squared plus cosine squared equals, yeah, 1. Okay, that comes from the Pythagorean theorem. Okay, if you want to know where that comes from, just let me know. Okay, but it's related to the sides of a right triangle in relation to your unit circle. Okay, that's the big one we have to know. So we're going to use that one when necessary if we have to. Okay, so let's take a look at this limit that eventually resulted in a hole. Maybe we can factor if necessary, or use a trig identity to help us rewrite it somehow. Okay, so is there anything we can really do to the top? Can you factor the top? Can you rewrite the top? 1 minus cosine? Anything you can do? Probably not. Okay, so we'll keep that the same. What about the bottom? We have a sine squared. Yes, you could write it as sine times sine, because you technically have 2 of them, right? But maybe we'll use this identity to help us somehow. What do you think, Dan?
If you subtract the cosine from the sine, then you would get sine squared equals 1 minus cosine squared.
Okay. So notice how this trig identity that we have to know, we can start to play around with it a little bit. We can move around some terms. If you were to subtract the cosine squared over, that would just leave you with sine squared equals 1 minus cosine squared. So if we have a sine squared, we can replace it with what it equals. Okay, that whole idea of substitution. So notice how we have one equation here with just cosines in it, which is kind of nice. Can we go any further? You said we can't do anything with the top, but now that we rewrote the bottom, can we do anything? 1 minus cosine squared. Maybe think about this as 1 minus x squared, because I know we're familiar with x's. Does it look like something that we can do?
1 minus cosine times cosine.
Right, it's a difference of squares. So we'd have 1 minus cosine as one factor, and then 1 plus cosine as another. So there we go, using that factoring technique. Notice how the 1 minus cosines would cancel. So we're just left with that placeholder of 1 up top and 1 plus cosine on the bottom. So even though direct substitution initially didn't work because we got that whole 0 over 0, let's try to plug in 0 now to see if we get anything different. Okay, so if we plug in 0 for the theta, cosine of 0, yeah,
1.
is 1. So looks like we're left with 1/2. So graphically speaking, we have a hole at this theta value of 0, but the height of that hole is 1/2. Okay, so same techniques. We're going to try some factoring, maybe fraction work if necessary, but the big thing is, since we're dealing with trig, you may have to use that identity. okay, to help you get around certain things. So that's one extra thing we can add to our repertoire. Okay, let's go ahead and check out some of these on the back. All right, let's go ahead and try some direct substitution, perhaps. Or maybe you guys just want to simplify the way the equation looks immediately before plugging it in. Because I don't know about you, but personally, figuring out tangent values is a little tricky for me. You know how you have to do the division and everything. So if I see a tangent in there, I'm going to want to try to get rid of it because it's not one that I'm personally comfortable with, and I'm sure you guys probably feel the same way. Okay, so maybe rewriting this would help us. Is there anything you want to do? Can we rewrite trig functions? Maybe tangent specifically, yeah?
You could have 3 sine over cosine.
Okay, so we have 3 sine over cosine instead of tangent. And we're still multiplying that by another cosine. So all we're really doing is changing the way tangent looks. By rewriting tangent, hopefully we realize the cosines would cancel, right? So instead of plugging in 3 pi over 2 into the original problem, which would still work, you could still do that, we could simply plug it into this new one, and it would still be the exact same answer. And notice how 3 sine is a lot easier to work with than 3 tangent cosine. Okay, so let's go ahead and try some direct substitution. All right, unit circle time, 3 pi over 2 is one of the ones we have to know as well. We're at the very bottom of the unit circle. What's the sine value at the very bottom? Yeah, -1. So it looks like our limit is -3. So not only can we use the trig identity to help us rewrite functions, but we can also use maybe relatable identities. For instance, we know tangent is sine over cosine. We can use that to help us rewrite things as well. We have some other ones also. When I look at this one, I don't know about you, but there's a lot of trig and a lot of thetas to plug in pi over 2, and I don't really know the secant value of pi over 2 off the top of my head. So let's see if we can rewrite this one at all. Can we rewrite what secant is? Yeah.
1 over cosine.
1 over cosine. And we have times another cosine, and that's all over 4 theta. Notice how the cosines would cancel, and we're left up with a 1 for that numerator. So actually, when you rewrite this problem, you're eliminating all the trig functions, which is nice. So now let's try to plug in pi over 2. So 4 pi over 2 is the same as 2 pi. We'll have 1 over 2 pi. We doing okay with these trig ones? All right. Let's try the next one. A lot of trig going on. I don't feel like plugging in pi to all of those, especially the tangent, because that's a little trickier to know off the top of your head. So let's try to rewrite this. We have cosine, and then instead of tangent, we can do sine over cosine. That's still all over sine. Notice how the cosines would cancel. So you're left with sine over sine. But what's sine over sine? Anything divided by itself? Yeah.
1.
Just 1. Alright, now if you tried to plug in pi, notice how we don't have a theta left to actually plug it into. So 1 is simply the value of your limit. You actually didn't even have to do substitution. You didn't have to evaluate any of the trig pieces. You just had to rewrite them. Okay, so don't get overwhelmed because it's trig. You just might have to work around it or use some properties or identities to help you simplify it. Okay? So those are kind of the easier ones. let's go ahead and take a look at this table of value at the bottom. So we already know direct substitution should always be tried first. Okay, that's always our first step. But we know that sometimes things don't really go the way that we want it to. So let's, for instance, take a look at this special trig function for a second. And we're going to go ahead and plug in these theta values into our function, and we're going to write out the values that we get from our calculator. Okay. Now, since we're dealing with trig, you need to make sure that you are in radian mode. So do me a favor and hit the mode button at the top first, and make sure that radian is selected in the third row. If you're in physics, I know Mr. Jones makes you do degree, so you will have to go back and forth and change that on your calculator if you use the calculator in his class, but in here it's always radian. Okay? So what you can do, if you want to hit second quit to get out of that, you can. If you want to take the time and directly plug these in for theta, you can. I think earlier this year I kind of showed you a quicker way to do that by typing this into the y equals and using the table option. Do we remember how to do that? Do we need a refresher? Yeah? Okay, so let's go to y equals. You can clear out anything that's in there, and we're going to type in sine of theta, but on your calculator you use x, and we'll divide it by x. Alright, next thing we're going to check is that table set. It's above the window button. Notice how it's blue, so you have to hit the blue button first. I don't really care what this screen looks like. The only important thing is that the independent variable is set to ask. So just make sure that's highlighted. Colton, can you do me a favor and just shut the door? Thanks. Okay, so now that the equation's in the calculator and we're telling the calculator we want to ask it specific x values, okay, independent variable values, we're going to go to the table button, which is above graph. And you may have values in there, you may not. Okay, if you do, you can just hit the delete button to get rid of them. But what we're going to do is go ahead and type in these independent x or theta values in, and it will automatically give us the related y values. So you can do negative 0.01, and you can write down that y value, negative 0.001, you can write down that value. Maybe you'll start to see a pattern after a while. Are we not getting those? Are we doing okay? Alright, so we're going to use this table to help us figure out these limits at the bottom. If we were to get closer to 0 from the left, notice how based on your table, 0 is found right there, kind of in the middle. So if we were to approach 0 from the left, what do the y values seem to approach or get closer to? Are we thinking 1? Okay. As we approach 0 from the right, notice how the y values also get closer to 1. So if we approach from the left is 1, approach from the right is 1, what is the limit as we approach 0 overall from both sides? 1, right? Because they match. Okay? So what's happening here is, what if we were given this problem just like that? Okay, sorry, it's at the bottom of the page. What if we were given it like that? You would try direct substitution first, right? And if we were to plug in 0 up top, sine of 0 is 0. And if we were to plug in 0 at the bottom, we would get 0. We know there's a hole, right? Okay. But if there's a hole, there should be more that we can do to get around that hole. The issue is when you look at your equation, can you factor anything? No. Can you use a conjugate? No, because there's no square root. Can you expand anything? No, because there's no parentheses. Can you use some fraction work? No, because we only have one fraction. Can we use any type of trig identity or rewriting to help us out? No, because this is not sine squared, and it's not like tangent or secant or anything like that. So if we go through every single option that we've discussed and nothing works, how the heck do we get around that issue of the hole? And that's when a calculator might be necessary. But right now, okay, now that we've used a calculator, we know that this limit will always be 1. So what we're eventually going to talk about is how we're going to have to just know this fact. Okay, we'll write it down on the next page. But in order to help us out with more advanced trig limits, we have to know that this specific limit is always 1. So if you approach 0 specifically for sine over theta, the limit will always be 1. It's eventually just going to be something that we have to know. Okay? But we'll deal with that more in a little bit. Okay? Let's go ahead and check out another table. Okay, you can use your calculator again. This time we have to type in sine of 3x divided by 3x. Now make sure you put 3x in parentheses in the denominator. Alright, and you can go to that second table again. If there's anything in there, you can delete them out if you want to. Alright, and go ahead and type in your new numbers. Do we get the same y values from before? From the previous table?
Yes.
Okay. So let's go ahead and answer the limits down below. We're specifically checking again as we approach 0, which seems to be in the middle of the table. So as we come in from the left, the y values get closer to 1. As we come in from the right, the y values get closer to 1. So that means the overall limit must be 1 as well. So here's the thing. We use a different equation, but it still developed the same table and the same limit results. So based on what we've just seen, what can you anticipate or conclude about a limit that has this particular setup? Okay, where c is a constant, meaning some number. What do you think the limit's going to be as we approach 0 of sine of some constant theta value divided by some constant theta value? What's that always going to equal? It's always going to equal 1. Okay? As long as that constant value is the same in front of the theta variable on top and bottom, your limit will always be 1. In the first example, the c value was 1. In this second example, the c value is 3, but as long as they're the same, the limit will always be 1. So that's also something nice for us to utilize as we go through some more difficult trig limits. Okay, we're going to fill out another table, very similar again, but we have a different function this time. Let's go ahead and type in 1 minus cosine. Let's make sure it's in parentheses as well. And once you have it typed in, you can go ahead and fill in your table with your theta values. Do we know what that E stands for if it pops up on your calculator? Scientific notation? Okay, so you have to move the decimal place 4 spots to the left to get that value. So that would be negative 0.0005. That might show up a few times. Alright, so let's use this table to help us figure out these limit values at the bottom. We're still approaching 0, so that's somewhere in the middle. As we approach 0 from the left, what do the y values seem to get closer and closer to? 0. As we come in from the right, the y values seem to get closer and closer to 0 as well. Just from the left, they're getting closer to 0 from the negative side, whereas from the right, they're getting closer to 0 from the positive side. So if both individual or sided limits are 0, that means the overall limit is 0. Okay. Again, if we were to try direct substitution on this equation, cosine of 0 is 1. Plug in 0 down below, we would get 0 over 0. Okay, so we have another hole, which means we could try to work around it, but again, if you look at your function, you can't factor anything. There's no square root for conjugates. There's no fraction work, because we only have one fraction. There's no parentheses for us to expand, and there's no trig way to rewrite it, like using identity or some equivalent fraction. Okay, so again, getting around this hole is going to be a little issue. Like the last one, we're eventually just going to have to know that this limit is 0, because it's going to help us with more difficult ones. So at the bottom of this page, we're going to write down the 2 trig functions that we have to absolutely know. Okay, so the first one is the limit as theta approaches 0. Oh, we can't see that. Okay, the limit as theta approaches 0, if we had sine of some constant theta divided by some constant theta, we said that was always 1. Okay, so we have to know that one. And then the other one we just did on the calculator was if we have 1 minus cosine of some constant theta. I know we didn't really do the constant part, but it would still work out to be the same if we did explore that a little bit more. So as long as those constants match each other, just like in the sine example, this one is always 0. Okay? So we have to know these. These are the tricky limits that exist, even though you can't continue to solve them by hand using some algebraic techniques. Okay? So these are the ones we have to know. We're going to use those tomorrow to take a look at some trig examples on the back. Okay, trickier trig ones. We doing okay? All right, we'll stop there for today.